Frank is the president of the BPAA, and he and I are both members of BARN. And so let's see if I can. So I want to briefly do what I've done in the past, which is review the last session. And that was about the full spectrum. And we talked about the frequency limitation of the eye, the fact that it can only see in what we call the visible. But that electromagnetic radiation is there, and it has wavelengths and frequencies, which is how you characterize it. And the electromagnetic spectrum is the range of frequencies or wavelengths that exist in electromagnetic radiation, excuse me, that run from very low frequency radio waves all the way up to gamma rays. And then we talked a little bit about emission and absorption spectra and how each element has a unique spectra that serves as a fingerprint to identify it, which I think is a miracle that you can go and, as I said before, I keep stumbling on this, but you can look out and take a spectra and find out, oh, there's oxygen way out there. There's oxygen out there. Isn't that cool? And machines we use to do that are called spectrographs. And then we talked about the redshift, which is very important for tonight's talk. And we had a video on detectors and how we've gone from the eyeball to glass plates to CCD detectors and what change that has made. And then another one about seeing the invisible, which talked about a video, which talked about the wide range of the electromagnetic spectrum that and the ways we have for seeing what we otherwise wouldn't be able to see. And then a method for visualizing magnetism, which is the Zeeman effect. If you want to, have a name dropper at a cocktail party, you say you've learned about the Zeeman effect. But and then we talked about space telescopes for high frequency research, and we've talked about last week we talked about exoplanets and how they can be detected using spectra as well as transit phenomena. So where we are, since we talked a few weeks ago, they've discovered another black hole. Can you see this cartoon?
Yeah.
Yeah, it's a photo of a black hole. Anyway, before we go on, I wanted to back up slightly and talk about the supernova, because again, they play a role in tonight's conversation. As stars go through, if the star has about more than 1.44 masses of our time, well, 1.44 times the mass of our star, it has, sorry, that's my daughter. She can't talk to me now. Higher than 1.44 times the mass of our sun, it will go through an evolutionary process where it will burn up its hydrogen, and it's the hydrogen that's burning that's going on inside that's pushing an outward force, which is counterbalancing gravity. When that hydrogen gets used up, the gravity takes over and starts to compress the remaining material and compresses it so that it goes through a very rapid nuclear reactions, which result in a few instances, all the other elements being created up to iron. And then the resulting explosion blows off this huge cloud. This is the Crab Nebula, which was observed by the Chinese in 1054. And it's about 11 light years in diameter. And what was left over after this explosion was a neutron star, where all the protons and electrons and neutrons got squeezed together by this gravity so that everything behaves like a neutron that's in the middle of it. And that neutron star is 18 miles in diameter, and it rotates 30.2 times a second. So this sucker really spins fast. And but it's a little bit bigger than the size of Manhattan. And that gas that's around it is moving away at 930 miles per second. And the interesting thing about this Crab Nebula, other than being beautiful, is that it radiates in almost all the wavelengths. So you can observe the Crab Nebula in radio wavelengths, infrared, the visible light, ultraviolet, X-rays, and even gamma rays. So it runs the whole gamut, as they say. And so it's very interesting. It sort of reinforces this idea around the spectra and our ability to detect things based on their wavelengths and colors. So this session is called Looking Back. It's the Big Bang and the Expansion of the Universe. And in session 3, we just went over this, but we learned how we can use spectra to identify the composition of what we observe and whether the objects are moving towards us or away from us and how fast. That's the redshift. But what we didn't talk about was how do we find out how far away they are. So I kind of like this image, the guy's peering out through the celestial sphere and wondering what's out there and how far away it is. But first we need to talk about some units of speed, distance, and time. And you probably all know this, but light travels at 300,000 kilometers a second, which is 186,000 miles per second, which, to put that in context, is about 7.5 times around the Earth in a second. The light will move. And the distance to the sun's 149 million kilometers. And so if you take 149,000 and you divide it by 300,000, turns out that it takes 499 seconds or 8.2 minutes to get for light to get from the sun to us. And the speed of light is a constant, so we can talk about distances and in terms of either kilometers or in terms of time, like 8.2 minutes. And astronomers have chosen to use light-based time as a measurement of distance rather than speaking in terms of kilometers. The numbers get too big if you're messing around with kilometers. And the distance, so you got 8.2 light minutes for the light to get from Earth from the sun to the Earth. And in the Earth and the sun as an astronomical unit. So it's an arbitrary thing, but it's a piece of a length of something that we can grasp. And just for the fun of it here, the astronomical unit distances of various things. The sun, of course, is at 0, and we're at 1. And Jupiter is 5.2 times of our distance from the sun. And Uranus is 19.2, and Neptune's a nice even 30 times farther away from the sun than we are. And then, Pluto has this big wide range. It's a very elliptic orbit. And probably another reason why it got demoted, because it really doesn't fit the pattern of the other planets. And the Voyager spacecraft that we launched quite a while ago is now 150 astronomical units away. So it's really scooted out there a long distance. But now we talk about really big distances. And as I said, the distance from the Earth to the sun is an astronomical unit. And that's kind of a nice solar system yardstick. But it takes 4.37 years for light to reach the nearest star. So for these large distances, we don't want to use meters or miles, and so we use light years as our yardstick. So the nearest star is 4.37 light years away, and that's not time, that's distance. Time and distance are interchangeable. And also,
so far away.
That what we observe now happened in the past. The light that's coming to us from this nearest star left that place 4.37 years ago, and things that are 13 billion years away from us, the light left them 13 billion years ago. So how do we measure these distances? And there's a couple methods. One's called the parallax, and another one is brightness, and makes use of what's called the Hertzsprung-Russell diagram, which I'll explain briefly. And we use Cepheid variables, which were discovered by Henrietta Leavitt. We'll learn a little bit about her. And then we also use as a distance measurement the light curve from a type 1a supernova, which we'll also talk about, but I wanted to mention the supernova, the first of this, so you understand what is going on in those big explosions. So let's talk about parallax. And there's a little, what I've done is there's a video that goes through each of these measures, and I'm going to, I've clipped it, and it'll just stop abruptly and then pick up and stop abruptly and pick up. And it's a little choppy, but it gives you a better explanation than I can do with my words.
Thanks to Squarespace for sponsoring today's video. You may have wondered, with the vast distances between objects in space, and with the lack of a tape measure that big, how can scientists be sure they know the distances between us and other celestial bodies? Well, there are a few methods available depending on how far away the object is, each with a varying degree of accuracy. The first method is the most accurate, and in fact gives us very precise measurements. This is the parallax method. For those of you that don't know what the parallax effect is, it is where nearby objects appear to move more compared to objects far away as you travel parallel to them. For instance, when you look out of a side window in a car, everything close by whizzes by, but objects in the background stay reasonably still. How does this equate to measuring the distance between stars? Well, Earth orbits the Sun, taking 6 months to reach from one side to the other. Scientists can look at a star and record its position compared to distant stars beyond it. In 6 months' time, scientists can again record where the star is. Because we know the diameter of Earth's orbit is roughly 300 million kilometers, using simple trigonometry, we can work out the distance to the star. Is the star close to us? Then the differences in its apparent location will be much bigger. Is it further away? The star's position will only change very slightly because the angle is much smaller. This method works up until about a distance of 400 light years, as beyond that the change in its apparent motion can't be measured anymore. Earth's orbit would have to be a lot bigger before you could use this method for farther distances, which is unfortunate because most things in space are further than 400 light years away from us. But thankfully there are very clever scientists out there that have come up with another method to judge distances without having to use trigonometry, although it should be mentioned that this method is slightly less.
He's going to say less accurate. So we've talked about distance measurement, and we talked about the astronomical unit, and we talked about light years, and I'm now going to introduce another dimension that astronomers use. It's called the parsec, and it's related to this parallax method. You notice down here, here's a picture of the sun and the earth going around. And that distance we just learned is 1 astronomical unit. And so the distance to something, a star that is subtends an angle of 1 arc second, is 1 parsec away. So par as in parallax and second as in arc second. And you, I think, all know that a circle is divided into 360 degrees. Each degree is divided into 60 minutes, and each minute is divided into 60 seconds. So 1 arsecond is a very small angle. But astronomers use arcseconds all the time. They're trying to resolve things that are extremely small, and so they're used to dealing in arcseconds. So a parsec becomes a nice convenient thing, and by the way, it turns out that that's about 3.3 light years. And our astronomers will talk about a parsec or 20 parsecs or 100 parsecs. A lot of things you're looking at are in the millions of parsecs away, so they're really far away. But so you got light years and parsecs. Now, the other way to measure things is how bright they are. We talked about luminosity and brightness in one of the earlier slides, and you've seen this diagram before, but this again is referring to this inverse square law. If I knew how bright this thing was, that's out here at this thing, what its absolute brightness was, I could calculate its distance from a ratio between its brightness, if it was right here, and its brightness that we observe. And so the intrinsic brightness is the luminosity, and the apparent brightness is its apparent magnitude. So it is possible to measure the brightnesses of objects by various means. And now we're going to introduce a really interesting but a little bit difficult concept. Hertzsprung and Russell were two astronomers in the early 1900s who independently came up with this same idea. If you look at a whole bunch of stars, which they had been doing, and you look at their spectra, you find that there's a class of stars that are sort of in this M range, where their temperature is about 300,000 degrees at the surface, and then K stars are 400,000 degrees at their surface, and so forth up to an O star, which has 30,000 degrees. So there's about a 10 to 1 difference here in temperature, and the temperature is related to the brightness. So if I find a star out here that's about this color, I'm going to know that it lies somewhere in this region right here. This is what this band was that they were able to calculate by observation, just fill in the points, so to speak. And so they could get the absolute magnitude of that star off of this left-hand side of the chart, and that would tell them how bright that star was, and then you can measure its intrinsic brightness against its measured brightness and use the inverse square law, and lo and behold, you get a rough approximation of its distance. I should point out that the sun, this is called the main sequence down here, and the way you know how well, I'm not going to get into this too much, but you study a large population of stars and you'll find that the bulk of them lie along these curves. Now there's some exceptions up here which are supergiants and giant stars, and they have different color temperatures and different sizes, but most stars lie along here, and our sun sits right here. And eventually what's going to happen to our sun, since it's only one solar mass, it's going to burn up its hydrogen, and then it's going to shrink, and the outer shell of it is actually going, the center is going to shrink, and the outer shell of it is going to spread out almost out to the Earth's orbit, and then the material is going to drift off into space, and what's left over will, on this diagram, move down into this area. It'll be cooler, and it'll be in this area where you find old stars that moved off this so-called main sequence. They don't physically move that way. It's just that they become in a different category as they age. So now let's go and talk a little bit more about that.
It seems that stars tend to follow a pattern, which can be seen on this chart. Main sequence stars, which make up the majority of stars in the universe, can all be found somewhere along this band. Their temperature corresponds to their color, and most importantly, their brightness. Using stars that have a confirmed distance thanks to the parallax method, we can see how much a star dims due to the distance between it and us, and extrapolate that far beyond 400 light years. So, say we see a very blue star that we want to know the distance to. Once we know the star's precise color, we can tell how bright it would be if it were right next to us. We can then measure the star to see how bright it is from our perspective. Combining this with our extrapolated data, we can predict how far away the star really is. Obviously though, there is some margin of error in our predictions. This band is quite thick after all, not a precise thin line. So these two methods work for stars in our own galaxy, where they are still close enough to be resolved individually. But what about other galaxies? How do we measure the distances to them? Well,
all right, and we're gonna keep going with that here. So he's going to talk now about Cepheid variables, and we're going to learn about Henrietta Leavitt, who figured these things out. And so this is a little side trip into her contribution to science.
So these two methods work for stars in our own galaxy, where they are still close enough to be resolved individually. But what about other galaxies? How do we measure the distances to them? Well, we would have struggled were it not for the universe being kind to us by gifting us Cepheid variables. A Cepheid variable is a very special type of star that changes in brightness periodically depending on how bright it is. And some of these stars are very bright indeed, so much so that the changes in brightness can be detected by us all the way in a different galaxy. Timing the pulses in a Cepheid variable, we can know exactly how bright the Cepheid variable should be and how dim it is to us, allowing us to use the extrapolated data again to work out the distance to it and to the galaxy it resides in.
So actually that talked about the Cepheids, but not Henrietta
Space, the final frontier. It's very, very, very big. We know this because there are galaxies that are hundreds of millions of light years away.
Oh, I'm sorry. I was trying to get rid of that bar.
Space, the final frontier. It's very, very, very big. We know this because there are galaxies that are hundreds of millions of light years away. This brings us to the question of the day. How do we measure the great distances of space? Thanks to her contribution, I can tell you how it's done. By her, I'm referring to Henrietta Leavitt. In the early 1900s, Leavitt was working at the Harvard College Observatory. She was working as one of the computers whose job was to measure and catalog the brightness of stars. You heard right. She was not working with one of the computers, but she was working as one of the computers. Before the advent of electronic computers, people whose primary job was to perform complex mathematical calculations were called computers because, well, they compute. That's fair enough for me. So Leavitt's job was to measure and catalog the brightness of stars as they appear in the observatory's photographic plate collection. In case you don't know, these plates are the predecessor of photographic film. They are rigid and not exactly portable. Images from a telescope was recorded on these plates at various times. Leavitt's job at that time was to study variable stars. These are stars whose brightness, as we observe them from Earth, changes over time. They are not twinkling stars. Don't get that confused. Leavitt found thousands of variable stars and images of the Magellanic Clouds. By the way, these Magellanic Clouds are actually galaxies. They were called clouds because they looked fuzzy in the early days before powerful telescopes and before we had solid evidence of other galaxies besides our own galaxy. Among the variable stars that Leavitt found, she noticed that a pattern existed in some of them. The brighter stars appeared to have longer periods. That is, the brighter the star, the slower the brightness changes, or the lower the frequency. She later refined her work looking at data from Cepheid variables. They're variable stars whose diameter and temperature, among other things, changes periodically. She confirmed that there was a relationship between the period of these types of variable stars and their brightness. Now here comes the hot part. Yeah, that was a cheesy pun, but anyway. With the knowledge of this relationship, it's possible to determine the distance of a star. And it goes a little something like this. Since we know the relationship between the brightness and period of a Cepheid variable star, if we know the period, then we can determine how bright the star is, if we were next to it. This is the actual brightness of the star, or its intrinsic brightness as it's called. Now, compare that value with how bright the star actually looks from Earth, and we can determine its distance. That's because the brightness of an object decreases at a well-defined rate. By the way, the rate at which the brightness decreases is called the inverse square law. Check me out later for more info. Anyway, since we can detect the period of a variable star fairly accurately based on Leavitt's discovery, we now can determine the distance fairly accurately also. This relationship is now called Leavitt's law. Well, I saw that coming. I hope you did. To use the law accurately, you'd have to, of course, take into account things like dust that could diminish the star's brightness. The period luminosity relationship for Cepheid variables made them the first standard candle in astronomy. A standard candle is an astronomical object whose intrinsic brightness is very well known. Has nothing to do with an actual candle. Do not ask for them on your next romantic dinner date. The The standard candle allows scientists to compute the distances to galaxies if they can detect a Cepheid variable within them. Galaxies that are too far to be measured with the best method at the time could now be measured. Now, that's far out. Yeah, I had to say that.
Okay. So we have time here for a little break to talk about distance measurement. There's yet another way we're going to measure distances, but these are the three most common ones for most astronomical work. Any questions or comments about that? I guess not. Hearing none.
No, I'm curious.
Yeah.
Valerie, go ahead.
Oh, hi.
What makes those pulsing stars pulse, or maybe pulse is the wrong word, but flashing, whatever.
Yeah, I'm glad you asked that question. It's what happens is the stars, I don't know how this gets initiated, but a star will expand, but when it does that, it cools off a little bit in the middle, or everywhere actually. And then that means that the outward pressure from the burning fuel decreases, and so gravity takes over and it shrinks down. And when it shrinks, it overshoots a little bit. And then as it gets smaller, it heats up more, and that starts more fusion, and it expands and it contracts and expands and contracts in a very periodic way. Lots of variable stars do this, but this particular type of variable, the Cepheids, have this relationship between the brightness and the period. Other stars are variable without seeming to have a relationship like that. But the idea is that it expands, cools, contracts, overheats, expands again, and so forth. That's what's going on in a Cepheid variable.
And they differ from other stars. I'm looking on Wikipedia right now. They differ from other stars in the amount of helium that they contain. And the helium is what causes the behavior that Peter just described.
That I didn't know. Thank you, Frank.
Mm-hmm. Oh, I wondered.
So let's talk about the expansion of the universe. And first I'm going to go back to some history that's fond to me. Mount Wilson, well, let me start. George Ellery Hale was a guy at the turn of the last century who was a solar astronomer, and he caused the Yerkes Observatory 40-inch refractor that we discussed in session 2 to be built there. And then he wanted a better place for his solar observations, so he came out to Pasadena and went up to Mount Wilson, which is at 5,000 foot elevation, said, hey, this would be a great place for an astronomical observatory, and he caused to be built a couple of solar telescopes up there, but he also then caused this 60-inch telescope to be built, and he incidentally helped found Caltech, and Caltech and the Carnegie Institution of Washington, which is now the Carnegie Institution of Science, collaborated to form Mount Wilson. And so this 60-inch was the first astronomical telescope that was built up there. And on the left is a picture of the Orion Nebula taken by George Ritchie, who's the gentleman who figured the mirror in the 60-inch telescope. And this was the first image that was taken by that telescope. And I was fortunate enough to be able to go there in night of February 10th and 11th in 1951, before most of you were born, and take this 4-minute exposure and guided to that on the 60-inch telescope. And a couple things that are interesting about this. One, of course, it was just a heck of an experience for an 10-year-old. But if you notice, there's a lot more detail in Ritchie's picture than there is in mine. And this has to do with what we learned earlier. The amount of exposure brings out more and more detail. And Ritchie clearly took more time taking his picture than I did. And I think Alan Sandage took me up there, and he knew that I would make footballs. You guide by turning little knobs and keeping a star centered in it. And if it drifts around, you'll start to make images that look like footballs. on your thing. So he didn't want me to have a football image, but as a result, it was fairly underexposed. So that was on the 60-inch. But now there's a picture of Orion taken from the backyard of Stephen Rule here on Bainbridge Island using a 10-inch telescope and a CCD camera. And you can see the huge change in technology that's available and the wonderful photographs that can be made by amateurs now. And so things have changed a lot. But back to the story. The other thing that Hale did was to get the 100-inch Hooker telescope built there. Hooker was a local industrialist in Los Angeles, and he twisted his arm into helping finance this telescope. And that was completed in 1917. And in 1927, Edwin Hubble sat down at the 200-inch and started taking a bunch of pictures. And he began to use Henrietta Leavitt's Cepheid variable information, and he looked for Cepheid variables. And when he saw them and measured them over a period of nights and days and weeks, he could see what their period was, and from that he could infer their brightness. And from that he realized that Andromeda was not a part of our galaxy, in fact was too far away and had to be a separate object. And believe it or not, up until that time, that was still an argument whether galaxies weren't part of just our Milky Way. And Milky Way was it, that was the universe. But it's not so, and he found this by measuring the Cepheid variables. So I throw in this cartoon. Never mind, I found the new galaxy. It's always in the last place you look, isn't it? So the other thing that Hubble noticed is that galaxies that were similar to each other but apparently farther away had their spectra shifted towards the red. And no matter where he looked, he saw that the galaxies that were smaller and farther, appeared farther away, in fact, had their spectra shift more and more to the red. And he thought, that meant that they were moving away faster than the nearby ones. And so he interpreted this to mean that all the galaxies were moving away from each other, and this meant that space itself must be expanding. And that's a pretty monumental idea. Remember, Sandage said the universe is an idea. So this rate of expansion of the universe now is known as the Hubble constant. And I got a way here that I found to visualize this that may make this seem more sensible to you. Hubble's law can be thought of two ways, either that all the galaxies are flying apart from each other, or the space between the galaxies is expanding. And the other thing is that there's no special place in the universe. It's meaningless to ask where we are expanding from. Everything's moving away from everything else. There's no center. And so if you look at this raisin bread dough, when it hasn't risen yet, there's various raisins here that are spaced different distances away. This guy's at 1 centimeter, and this is at 16, and this one's 5 centimeters away. And you let the dough rise, and it goes from 30 centimeters long to 60. And so this distance between here and here went to 32, and which means that it doubled. And this one went from 5 to 10, and it doubled. But in order for this distance to double, it had to go twice as fast as this one did. And so the rate of expansion, this one looks to an observer sitting on A like that raisin is moving away from it faster than this raisin that's nearby at B. And I don't know whether you're getting a visual sense of that or not, but that's really what this expansion is all about. These things are all just moving away from each other, and there's no center to it. If you were standing on D and you look back at A, you would think that A was moving at the same rate away from you as it appears from you to be looking back at D. That's equivalent. Any questions about expansion before we go on? This is a tricky concept.
Yeah, can you hear me?
Yeah.
So different objects are moving at different speeds?
The farther away they are from us, now this is, we're talking about galactic scales, not a pencil
Right.
on your desk. The farther away they are, the faster they're moving away from us.
Okay, that part I get, but I guess the image of the raisin bread is bothering me.
Well, what he's trying to show here is that in the time it took for this dough to raise, it went started 16 centimeters away, and during that time, this went 32 centimeters away, but the nearby raisin only went from 1 to 2. So it means that in the same amount of time, the nearby raisin is not going as fast as the
Okay.
one that's farther
Okay.
away.
Okay.
And it's kind of a leap of something to figure that out, but that's what's going on.
Is raisin a standard astronomical unit?
Well, I think the chocolate chip is actually a better one. Thank you for that, Vinny. So,
Well, I have a question.
Yeah.
So in your raisin bread analogy, everything's doubling. So
Yes.
is it possible that some things are doubling and some things are tripling, like, or is they're all consistently doubling?
They're all consistently doubling, and of course, in a certain amount of time, they wouldn't necessarily double. It depends on the amount of time. But that rate is the Hubble expansion rate of the universe. That's what this number is that everybody's been looking for, is to figure out the rate of expansion of the universe.
Okay, thank you. I understand.
So you saw the picture of Hubble by the 100-inch, and this is my good friend Alan Sandage, also by the 100-inch. And he was a protege of Hubble. He knew him and and sort of sat at his knee, so to speak, to worry about the Hubble constant. And he spent most of his career doing that. And well, I have some interesting stories about that, but that would be another lecture. So let's go on and talk about supernova and how we can measure really large distances. And I should mention that supernova as standard candles came into understanding fairly late in Sandage's career. And so he did all his work with Cepheids and the brightness, the Hertzsprung-Russell diagram and things like that. But the Cepheid variable changed things, and there's one more thing coming up after that.
Complicated and less accurate. With galaxies billions of light years away, you have to start taking into account the expansion of the universe and redshift. And the distances make seeing the galaxies at all very difficult, as they require long exposure photos, which will blur the variations in light produced from Cepheid variables, assuming they are bright enough to be seen at all. However, the universe has given us one more measuring stick to work with, type 1a supernova. These are a very specific type of supernova, where in a binary star system, a dense white dwarf starts to cannibalize a larger red dwarf. Once the white dwarf hits a critical mass, the star becomes unstable and undergoes a runaway nuclear fusion reaction, producing an extremely bright event that can rival an entire galaxy in brightness. Because these supernovae always happen to a white dwarf that hits a very narrow range of mass, the rise and fall of their brightness is very predictable. And given they are very bright events, they have been used to measure distances of up to 13.2 billion light years. However, there aren't always these type of supernova going off, which means if scientists want to use this method, then they need to be very patient. There are a few other methods out there too, but this covers the main ones. To me, these are incredibly clever methods to measure distances, and credit to the scientists who came up with them in the first place. The only sad thing about realizing how far away everything is knowing how hard it will be to cover those distances should we ever want to explore beyond our own solar system. Here's hoping for more bright minds to come to the rescue in a few generations' time.
So a type 1a supernova like that is 5 billion times as bright as the sun. I mean, they are really bright objects. So there are these 3 steps to the Hubble constant. And as I said, my friend Sandage worked mostly in this area. So the Cepheids that Hubble himself looked at, and then Cepheids out here in these galaxies, which Sandage spent a lot of time on. And then later on, when we got the Type 1a supernova, and he did some experiments with the Hubble telescope, detecting supernova at these very large distances. But these have been the primary ways in which we've been trying to figure out the size of the universe, the age of the universe, and the rate of expansion. Well, that you've seen before. In fact, that's what's right behind me, so I'll skip that. So, questions about standard candles and the expansion. Okay.
It's a
Well,
bright class.
Yeah, it's also a small class.
Has the expansion been the same since the big moment of the Big Bang?
I am going to show you that.
Oh.
You're ahead of the class just a little bit.
Okay.
If you have this expansion going on, then the assumption is that there must have been a time when space was really small, or that is, say, when space and time and matter came into existence, and that would have been 13.82 billion years ago. And it's remarkable that we can now get that and describe that with such precision. There's some plus and minuses on that, but it's still a pretty accurately known number. But there's another effect that was discovered, which has come into play in all this. 2 guys by the name of Penzias and Wilson were working at Bell Laboratories, where Ron used to work, and they were preparing for the Telstar experiment, which is a satellite that Bell Labs was going to put up for communication purposes. And it was going to be using the microwave bands. And so they had this horn antenna, and they were trying to calibrate it because they were going to be getting the signals, and they wanted to know if they got a signal with some strength, what did that really mean in terms of the gain of the antenna. And they did everything they could, and they kept getting this noise, electrical noise in the antenna. And they'd look up and they'd look down, they'd look at the time open during the day, during the night. They always found this noise. They cleaned out all the bird poop, everything they could think of. They finally decided that this cosmic background radiation was what they were detecting, that it was something out in space and seemed to be everywhere, and it was at this particular range of microwave frequencies. And that turned out to be a Nobel Prize-winning discovery. And people have now mapped what the universe looks like in this microwave radiation. And this is, again, a little harder to visualize, but this is sort of a sphere unwrapped and doesn't have meridians or an equator or anything on it. But the thing that's remarkable about this corresponds to the universe having a temperature of 2.725 degrees above absolute zero. So it's extremely cold, but even though it's very cold, we can detect the microwave radiation from it. That's what Penzias and Wilson did. And so these orange colors are a little bit warmer than the blue colors, but we're talking tenths of a degree or less. And those, as far as anybody can tell, are leftovers. Well, no, never mind about that. We'll get to that later. But anyway, this cosmic background, microwave background, has been carefully measured. And so we now have a new thing to look at. We've got the Cepheid variables, we've got the Type 1a supernova, and we've got a movie about the cosmic distance ladder, which will include a little bit about the cosmic background, I hope, if I haven't forgotten.
Ever since Edwin Hubble discovered that the universe is expanding, there has been a great debate about the speed of this expansion, also called the Hubble constant. In 2000, scientists thought they had reached a consensus, with the Hubble constant at about 72. But since then, two methods of calculating the expansion rate have gotten farther and farther apart, and some scientists think it's too big of a difference to just be a statistical fluke. To calculate the Hubble constant, we need both a velocity and a distance. Velocities are easy. It requires measuring the redshift of a galaxy as it recedes. But distances are much harder. We need standard candles, objects that shine with an intrinsic brightness. That way, its observed brightness could be converted to a distance. The first method used to calculate the Hubble constant originated with Hubble himself. He started by measuring distances to nearby objects and working his way out. Hence the name, the cosmic distance ladder. The first rung is within our Milky Way. Here we measure the distances to Cepheids, pulsating stars that have an intrinsic brightness. Then we look to nearby galaxies that contain both Cepheids and another type of standard candle, Type 1a supernovae. These exploding white dwarf stars also have an intrinsic brightness. After calibrating these supernovae, astronomers can then move out to a third rung, to even more distant galaxies that only contain supernovae. Linking all these measurements, a recent study has pinned the Hubble constant at 73. Instead of starting within our galaxy and looking out, the second method looks back in time to almost the beginning of the universe. Here we find the cosmic microwave background, the radiation left over from the Big Bang. The CMB's subtle variations in temperature describe changes in the density of the universe right after the Big Bang. Instead of standard candles, physicists use the size of the tiny fluctuations as standard yardsticks. With these yardsticks, they can calculate what the Hubble constant would be today. Recent estimates are at about 68, significantly lower than the cosmic distance ladder's approach. Both camps hope to resolve this debate in the coming years with the help of new telescopes and instruments. But if the discrepancy in the Hubble constant remains, it could mean that our understanding of the expansion of the universe is missing an ingredient. That something happened between the Big Bang and the present. Maybe there's a neutrino out there we haven't discovered. Maybe the mysterious force, dark energy, which makes up a significant portion of our universe, can change in strength. Or maybe subtle flaws in one or both approaches to the Hubble constant are giving us the wrong answer.
So the Hubble constant, from data gathered from the Planck satellite, which studied the cosmic background radiation and its deviations in temperature, have come up with this number of 67 kilometers per second per megaparsec. Remember, we defined the parsec, and I told you we'd talk about megaparsecs. So what this says is that if you go out a megaparsec away from us, which is 3.3 million light years, something will be receding at 67, but if you double that, it's going to be really receding even faster. And so we've got this number pretty well narrowed down, but as this previous video said, we don't know quite what to make of the discrepancy between these two methods. And to go back to my friend Sandage, who said that the universe is an idea, he would argue that it's that lower number, around 67 or even lower, and it's gonna be a scientific discussion or fight, if you will, for quite a while. But now back to Vinny's question about the early universe. You saw this diagram briefly in the movie. And I'll do my best to explain this, but I'm not sure I'll get it exactly right. But you go back to a time when the universe consisted of this little tiny singularity that had nothing but energy in it. And what we think of as space may have been there, but it's sort of irrelevant. And then this energy was suddenly released, and the space and time began at that time. And suddenly everything got bigger by a whole lot. And then as things cooled, because they cool when they expand, that leaves behind this cosmic background radiation. And then there was another period, which I'll show you more detail on another slide, in which you couldn't see anything. And then the stars and matter began to form, and now we find ourselves with looking back in time into all this early universe and noticing that the universe, the Hubble constant, appears to be changing a little bit. That is, we're accelerating our expansion. And I think that's still a controversial result, although most people don't, but I do. And I want to go back and look at that same type of diagram and notice these really small numbers here. This is 10 to the minus 32 seconds. That's 1 second divided by 10 followed by 32 zeros. Extremely short period of time in which all this energy that was released is going through some quantum fluctuations, which I'm not going to explain, and the universe inflates. And it needs to have inflated, not because we know it did, but because the way the universe appears now implies that it is flat from a geometrical standpoint, and that, oh, what was the other thing? Oh dear, help me out, Frank. Anyway, it inflated, and I've had a hard time understanding inflation, and I've had people explain it to me, and I don't know that I completely understand it. But nevertheless, it's an explanation that has come about because it fixes some of the problems in the way we think about what's going on here. But this is essentially time and space come into existence in this instant, and space gets as big as this so-called event horizon. If you think about it, and this is tricky, the observable universe is the only part of the universe we can know about. And by observable, if you think about light that's emitted somewhere in the, let me back this slide up. If light was emitted here out this long ago, and you, oh, how can I describe this? You can't see past this boundary because any light that is emitted outside here will never get to you before you've expanded away from it. Does that help? So the light's emitted from some source, but it's so far away that by the time it gets to you, it doesn't, because you've expanded farther away than it is. It never catches up with you. So there's a point, a boundary around this where the universe is observable. Maybe other things out there, but it's not observable because the light from it can't ever reach us.
So a way to think about it is that if you draw a horizontal axis through the center of that cone, that horizontal axis, either this diagram or the other one, Peter, either one works. But if you draw a horizontal line through that, that horizontal line is the Earth's timeline. We're on the Earth and we are the observers of this. And you know, the horizontal scale on this is time. And if you draw that horizontal line through the center of this thing, that's the Earth's path through time. And the upper and lower curves are the boundary of the universe that we can see from Earth's perspective. And as time goes on, we can see farther out. That's the widening of the cone at the right-hand end. We can see farther out simply because time has passed, enough time has passed for light from those regions to reach us. So when Peter says we can't see beyond that, it's because, as he said, the time that it takes for light to travel from those boundaries to us is longer than light can travel. Longer than the distance, I'm sorry, the distance away is farther than light can travel in that time. I don't know if that helps, but.
Yeah, it helps me.
Another point I want to make is that remember the loaves, the raisin loaf that was rising? At the left end of this, in that period of inflation, the left end of this diagram, space is expanding. You can think of it as the loaf expanding, not the raisins moving through the loaf, but the loaf itself expanding at a rate that is faster than the speed of light. That's what's implied by this period of inflation. In order for the universe to get from the singularity at the Big Bang to the size that we observe at when we look back in time at this 10 to the minus 30 seconds, in order for the universe to have reached that size, it had to have inflated at faster than the speed of light. So it's as if the loaf was expanding at a very, very, very high rate.
And the way I think of this is this time right here is the universe has only energy in it. You remember Einstein's E equals mc squared. That says there's an interchangeability between mass and energy. And at this time, it was all energy. And only a little bit later, this is only a microsecond, but some of that energy turned into what we think of as matter. That's the protons being formed in here. And then some fusion takes place and helium gets produced. And then things cool enough so that the microwave background radiation gets imprinted on space. And then neutral hydrogen forms out after that. And this area is kind of called the dark ages, because when before neutral hydrogen does, is this whole space is now filled with electrons and protons. And the free electrons don't allow light to pass through them. They absorb all the light. But when the electrons start to join up with the nuclei of the protons and form helium and hydrogen, then they get bound up in those atoms, and then all of a sudden the universe became transparent. And now the light that was right here at this cosmic background can begin to radiate out. It's not light in the visible sense, it's light in the microwave sense, but it can now become visible and measurable. So this is a tough subject. So I've got a video, which I think is a pretty good video that summarizes this. It's going to use some terms and stuff from atomic physics that we have not talked about, like muons and quarks and things like that, but you'll just have to kind of grasp it as best you can and see how it goes.
The universe is everything, from the tiniest particles to the largest galaxies, to the very existence of space, time, and life. But how did it all begin? The origin of the universe is the origin of everything. Multiple scientific theories, plus creation myths from around the world, have tried to explain its mysterious genesis. However, the most widely accepted explanation is the Big Bang Theory. The Big Bang Theory states that the universe began as a hot and infinitely dense point. Only a few millimeters wide, it was similar to a supercharged black hole. About 13.7 billion years ago, this tiny singularity violently exploded. And it is from this explosion, this bang, that all matter, energy, space, and time were created. What happened next were two major stages of the universe's evolution. Called the radiation and matter eras, they're defined by key events that helped shape the universe. First came the radiation era, named for the dominance of radiation right after the Big Bang. This era is made of smaller stages, called epochs, that occurred within the universe's first tens of thousands of years. The earliest is the Planck epoch. No matter existed in the universe at this time, only energy and the ancestor to the four forces of nature, the superforce. At the end of this stage, however, a key event occurred in which gravity split away from the superforce. Next came the Grand Unification epoch, named for the three remaining unified forces of nature. This epoch ended when one of those forces, called strong or strong nuclear, broke away. Then, the inflationary epoch began, during which the universe rapidly expanded. Almost instantly, it grew from the size of an atom to the size of a grapefruit. The universe at this time was piping hot, and
notice up here, the temperatures we're talking about, 210 to the 33. That's pretty hot. And the time that's gone by just to get this far is 10 to the minus 30 seconds, 10 to the minus 36 seconds. So this is all in an extremely short period of time that all this is taking place.
Churned with electrons, quarks, and other particles. Then came the electroweak epoch, when the last two forces, electromagnetic and weak, finally split off. During the next stage, the quark epoch, all of the universe's ingredients were present. However, the universe was still too hot and dense for subatomic particles to form. Then, in the hadron epoch, the universe cooled down enough for quarks to bind together and form protons and neutrons. In the lepton and nuclear epochs, the radiation era's last two stages, the protons and neutrons underwent a significant change. They fused and created nuclei. And in doing so, they created the first chemical element in the universe, helium. The universe's new ability to form elements, the building blocks of matter, cued the matter era. Much as the name suggests, the matter era is defined by the presence and predominance of matter in the universe. It features 3 epochs that span billions of years, the vast majority of the universe's lifespan, and includes the present day. The first was the atomic epoch. In this stage, the universe's temperature cooled down enough for electrons to attach to nuclei for the first time. Called recombination, this process helped create the universe's second element, hydrogen. This hydrogen, along with helium atoms, dotted the universe with atomic clouds. Within the clouds, small pockets of gas may have had enough gravity to cause atoms to collect. These clusters of atoms, formed during the galactic epoch, became the seedlings of galaxies. Nestled inside those galaxies, stars began to form. And in doing so, they cued the latest and current stage of the universe's development, the stellar epoch. The formation of stars then caused a tremendous ripple effect and helped shape the universe as we know it. Heat within the stars caused the conversion of helium and hydrogen into almost all the remaining elements in the universe. In turn, those elements became the building blocks for planets, moons, life, everything we see today. This ecosystem of everything was only possible because of the many stages in the universe's development. While countless questions about the origins of our universe remain, it's only a matter of time for some long-sought answers to emerge.
So, I really liked that video. Any discussion about that?
That's a great video, Peter.
Yeah, I think it is too.
Is there a link on there to that video so that when you send us the link to the lecture, we could, because that is a good one. That's
Yeah, I can do that. It's
Okay,
not on
appreciate it.
here, but
okay.
I can get it.
So
Thanks.
what's the theory on the size of this energy source that the Big Bang starts from?
It's speculation, but it's based on our understanding of physics. The only way you can make it work with the physics as we know it is to postulate that it was extraordinarily small. She said in that movie there was like a millimeter or two. That's 40,000th of an inch. It's sort of rice grain size. And it's hard to imagine that all the energy that's in the universe was at one time in that little tiny space. I don't think it's very easy to build up an image of how that could work. But that is what the physics explanation is. And all that early time that we're talking about there is all based on what we know about nuclear physics and the temperatures and the formation of things that we're learning from using accelerators. For example, we have accelerators on the Earth like at CERN, and we bang things into each other at very high energies, and we get the particles that come out of them, and we can discern what's inside protons and neutrons by these high energy collisions. Well, that gives us a clue about how things might have been at the early times, except that the numbers in terms of temperature and the units in terms of time, temperature is enormous and the time units are extremely, extremely small. But that that explanation you saw in the movie explains pretty well how the constituents, the matter constituents that are here in the universe now, came into being in that very short amount of time. And but it is speculative. You can't go back and rerun that program. You've got to just kind of figure out what fits the data the best they can. And one of the most important things is this relatively modern discovery of the cosmic microwave background, because all of a sudden we got a picture of what the temperature of the universe looked like over the whole span of the universe right after the Big Bang. And that leftover has all these clues in it that if you go and measure the distances between those hot and cool spots on that cosmic background radiation, then you can say, well, the only theory that will explain that is such and so. And so that gives you a tool for looking back at the very earliest times of the expansion of the universe, or the beginning of the universe. And without that CMB, we wouldn't know, we wouldn't be able to make the kind of speculation that this movie is making now. And there's disagreements about how to interpret this. I saw one video of myself a while ago, and I can't really explain it all to you, but I would just say that not everybody's in agreement about this yet. There's still more measurements to make and more to learn. But that's part of what's so fun about astronomy and cosmology, because there's an awful lot to learn.
So, Peter, we have a couple of hands up with questions.
Yeah.
Kathy, you want to go ahead?
Yeah, I had heard that there was a theory that, back near the Big Bang, that the speed of light might have been different. Can you talk about that a little bit, if you are aware of it, and maybe what that might mean to what we see when we start looking back that far?
Well, I'm not aware of that idea. I don't think that it makes much sense given what we know. And I think it would be one of those things that would be really hard to prove. You could build a big case around it, but you could never know if it was so. And I don't think the CMB, or cosmic background radiation, supports the idea of a variable speed of light. It does go back to this question of what is that expansion like? Frank said that the expansion seemed to take place at a rate greater than the speed of light. But one of the videos I was looking at said that, well, wait a minute, that you have the singularity, but that doesn't mean there isn't space around it. It's not space in the sense that we think of space, but there is something outside of that singularity. And this energy just suddenly goes and fills that very, very rapidly. And then time begins. And when time begins, space begins, because it's space-time. And then everything marches forward from that. And in the space-time that we live in, speed of light, as far as we know, is constant no matter where you are in that location. Any place in it. If you're on a galaxy that's receding from us, the speed of light there, when you measure it locally, is exactly the same as the number we would get here. That's a hard concept by itself, by the way. And
I'll add that there was a book published maybe 20 years ago or so that I actually have the book. I read it, and it put forth that that idea that the speed of light was variable over the life of the universe, but that idea did not get any traction, and it was met with a lot of resistance in the scientific community, and was never there was never any work done, or I should say there was work done that could not support that idea. So it was somebody's speculation, and but that's as far as it went.
Okay, thanks.
And let's see, Nancy has her hand up, or Tim, one of you has a question.
Yeah, actually got a couple of questions, but let me start with one that's very similar to the previous question. It seems to me there was some debate at some point as to whether the Hubble constant was spatially constant or might vary depending on where you are in the universe. Do any of you run across that? Do you know anything about that?
I do not, Frank may. I think, but I don't have an answer for that, Tim. I just don't know. I think that my friend Sandage would have operated all his life on the assumption that the Hubble constant is a constant, and that's what we're looking for, is this rate of expansion. On the other hand, I remember him drawing graphs of the Hubble constant as measured over at different distances. I mean, the distance measurements and the implied Hubble constant that had, and it's a nice straight line going out. And he kept wondering whether that line might curve upward, which would indicate the universe is going to expand forever, whether it just went out as a straight line or whether it dipped down, and which would imply some sort of closed universe. And his conclusion when he got the Crawford Prize and gave this thing was that the universe is flat and the curvature is zero. And lots of people still believe that as being the correct fact. But that's about all I know about it. I don't think there's any inference from what he was doing that it's changed per se. It's just, there is the question of whether the universe is closed, open, or flat. And the prevailing agreement now is that it's flat.
Sorry, go ahead, Peter.
Well, I was going to say the cosmic background stuff and other measurements have shown that the matter that we know about is only about 5% of the universe, and that there's this dark matter, which is another 27 or so percent of the substance of the universe, and then there's another the remaining, what is it, 70%. Is dark energy. And so then you start, that gives you another whole avenue for making postulates about what's going on with that stuff. Why we can't see this so-called dark stuff because, well, it's dark, it doesn't emit light. But we can measure its effect on galaxies. Stars rotate too fast around galaxies based on what we can see as the visible matter. And that includes radio waves all the way up to gamma rays. There's still not enough matter to account for the speed of rotation, gravitationally induced speed of rotation to be what it is. So that says there's got to be some other dark matter that makes up a part of galaxies. And then the other issue is that there is some dark energy, and the theory is there that this dark energy may in fact be pushing outward and causing the universe to expand more than it used to, which would imply the Hubble constant is in fact changing a little bit. But I don't know enough about that to give you the full scoop.
So the measurement of the supernovae, as we look back further in time, well, Tim, specifically to your question, to talk about it changing in time and versus changing in space is really not a distinction that you can make, because when we look at this time, we're looking at something that's close by us, so where it's in the same, roughly in the same space. If we look at something that's farther away, we are necessarily looking at it as it was some distant time ago as well. So we are looking back in time. And when we do look back in time or look out farther into space, same thing. But we see these supernovae that that are standard candles, but their brightness is not as bright as they should be if the universe is behaving in the way we think it is. In other words, behaving as with a flat rate of expansion. And so it is the presence of these anomalous supernovae that has led to this to support this idea of dark energy. We don't know what it is, but we see an effect, and we see something that we can't explain, and so the idea of dark energy is an attempt to explain what we're seeing in the behavior of those supernovae.
My friend Sandage would argue, as he did with lots of people, that may be due to an extinction coefficient. You've got matter between us and those things that are 12, 13 billion years away, and they're not as bright as they should be, but have you accounted for all the things that might have absorbed that light as it moved towards us during this last 13 billion years? And that in itself could make things be fainter. It's a little bit like you guys in California. Well, nobody, I guess nobody's from California, but you're looking through smoke, things look dimmer. Well, you've all seen the sunset. It looks dimmer when you have stuff between it. So there's an argument that if you don't know or can't take into account what might be reducing the brightness of those, it may not be a real effect. It may just be, I mean, it's not a cosmological effect. It's a simple mechanical effect.
And that is the subject of intense research right now.
Yeah, sure
and
is.
A lot of these new telescopes that are coming online will explore that very question.
Excellent.
Okay, any other questions?
Yeah, if no one else has a question, I wanted to ask a second question on the timeline, the universe timeline, sort of the cone slide that was 2 or 3 slides back. How far back, given that one, given the energies that we've managed to generate, I think the Large Hadron Collider is probably the most energetic collider we have. Given the energies that facility is capable of, how far back in that timeline can we reconstruct using those colliders?
I don't know the exact thing. We're nowhere near the kinds of energies that are being talked about in this area here. I mean, we do have some we can mess around with nuclear fusion, and we can bust apart and see quarks, and recently we think we've seen something called the Higgs boson, which is a field that supposedly accounts for gravity. But what I've read about it is that you can't on a ground, and we don't have a way with accelerators here on Earth to create anything close to these conditions that existed back in there. We can hypothesize, but we can't yet generate those conditions. And I don't know your answer. The answer whether the hadron is looking at what was occurring in this area, or this area is certainly looking at what can happen out here, but I don't know how close back in this curve we can get.
Well, in that video that you showed, Peter, that talked about the 4 forces of nature, and it talked about the gravity being separate from the other 3. The other 3 were unified in the early universe, and as the universe aged, those and the energy density went down, those forces separated, and now we see them as 4 individual forces. But we've been able to reconstruct the combination of the 3, the strong, the weak, and I can't think of the third one. But the search right now is the search for the way to unify gravity with those other three forces and come up with a true grand unified theory that explains everything. And that condition existed in the early universe, and we can't, our accelerators today can't recreate those conditions. So kind of to answer your question, Tim, we can't go back that far, but we can get back almost that far enough to explore the unification of the three forces, but not far enough to explore the unification of all four.
Okay, thank you. And then from that same slide, I think Frank mentioned, or Peter mentioned this, but there's sort of an absolute limit to how far we can look back with the electromagnetic spectrum, and that's about 380,000 years back.
Yeah, that's the cosmic background radiation that we can see is as far back as we can go. And so the rest of this is, again, based on our understanding of nuclear physics, and it makes a pretty good story based on that movie. And that
was a great little clip.
Yeah. Was.
Yeah.
So Peter, you've got about 5 minutes till 8:30.
Does anybody want to learn a little bit about gravity waves?
Sure.
All right. Well, I've got a few more minutes of that, and then we would go, if that's all right with everybody. And I think it's a little bit relevant. Let's see. I gotta there. So Einstein's theories predicted that there would be gravity waves. That is, space and time and gravity interact in such a way that just like we have electromagnetic radiation, he predicted that we would have gravity radiation. And he also knew that it would be an extremely small force. But he did realize that gravity would be strong enough to bend light, for example. And that was observed in eclipses. Star that ought to be in a certain place in the sky, when you go and have a total eclipse of the sun, you'll see that star is not where it would have been if it hadn't been very close to the sun on its way, that light on its way to us. So the gravity is bending light. And if two very massive objects interact with each other, they can actually distort space and time, and that becomes a ripple. And
gravitational waves were predicted by Einstein almost 100 years ago.
Well, a gravitational wave is a ripple in the fabric of space and time. It's produced somewhere in the distant universe and travels across the universe.
When any massive object moves, it's changing the nature of space-time. That's what Einstein told us.
So you have a motion that stretches space in one direction and compresses space in the other direction.
Nobody really believed at the time of the prediction that you could ever detect them because the size of the effect is so small.
It was what we call a chirp, and it was strong.
Everybody thought it was a fluke. It was too good.
And I thought, my God, this looks like it's it.
Oh my gosh, this is real. It took us 25 years and 2 detectors to finally detect a gravitational wave. We have interferometers, one in Hanford, Washington, one in Livingston, Louisiana, to detect the stretching and compressing of space.
We literally look for changes in the space-time distance in our instruments as the gravitational wave goes by.
And the gravitational wave pushes them together and apart by 1/1000th the diameter of the nucleus of an atom. No wonder it's taken so long to pull this off.
However, what's even more remarkable about this is what we detected.
We have observed gravitational waves from 2 black holes forming a larger black hole.
For the first time, 2 black holes
spiraling together, coalescing, merging, creating wild oscillations, a storm in the fabric of space and time.
They're moving at the velocity of light, damn near that velocity, 30 solar masses moving that fast. I mean, they're putting out incredible amounts of energy.
And when they collide with one another, they produce a bigger black hole, but they also produce gravitational waves. And in that process, about 3 solar masses just disappears and goes into gravitational waves.
Oh, it's going to be amazing. We have always said that this is going to be a field called gravitational wave astronomy.
Gravitational waves carry information that you can't get from any other way. A supernova, 2 neutron stars colliding, even the Big Bang itself, the beginning of the universe, all produce gravitational waves.
This first detection by LIGO is the very first step. It's just the start of the story nature is about to tell us.
I would love to see Einstein's face. I mean, he would have been as dumbfounded as we are, because it's a wonderful proof that all of this incredible stuff, the strong field gravity, is in his equations. Just imagine that. To me, that's a miracle. It settles the question for astrophysicists. Do black hole pairs form? Yep, we got one.
So guess what? There's spectra associated with gravity waves. And there are short ones and there are long ones. The age of the universe is you can think of the universe itself being a giant gravity wave. But you can also have these events which they can detect with the LIGO, which is what's going on here. And there's a hope someday we'll actually put a LIGO-like device up in space, a couple of them, and they will have a long baseline length, and they won't have any influences from terrestrial gravity. The LIGO, they have to worry about whether a truck is going by because it'll bounce the ground around, and that's way too much motion for them to be able to tolerate in their measurements. So they have to isolate this from everything. But if you put one up in space, it'd be really cool. Then you could get some good measurements. But my point here is that LIGO is another form of astronomy instrument. You can actually use, this is a telescope, and the telescope is looking at the deformation of space-time caused by huge masses interacting with each other. And just like other forms of energy, as it moves through space, it has this inverse square law. So if this gravitational effect takes place a long, long way from us, the strength of that signal when it finally gets to us is very weak. And it's only sort of with these instruments, things that happen relatively nearby, that we're going to be able to detect. But there's plenty of it to detect, and they are frequently I don't know how many good solid detections we've gotten, but quite a few.
14.
14?
Yeah.
Okay. So I'm going to sum up here. In session 1, we talked about seeing and noticing the planets, stars, the rhythms of nature, the early observatories and how important they were for predicting events which were related to weather, not to weather, but seasons, and the mythology around it. And then constellations, the early history of astronomy, what people could observe with their eyes about the solar system, and we discussed a little bit about star formation, and then there was a movie about our place in the cosmos. And the second session was extending the eye. We talked about the eye itself and refractors and reflectors, and this good old inverse square law again, and the advantages of big telescopes and how adaptive optics are important for big telescopes that are ground-based, and what some of the future of optical telescopes would be, and of course a little bit about radio telescopes. Then we shifted gear and started talking about the frequency limitation of the eye and the electromagnetic radiation, wavelengths and frequencies in the spectrum, unique spectra as fingerprints, and all this I talked about at the beginning of tonight. The emission and absorption spectra and spectrographs and the redshift. and finally detectors. And then this other video on seeing the invisible and exoplanets and so forth. And tonight we've talked about supernova and distance measurement units like the astronomical unit, the parsec, light year, those things, and methods of measuring distances with the standard candles and parallax and the HR diagram and standard candles already said, the supernova and the Cepheids, and then Hubble and Sandage, and the expansion, and the cosmic background radiation. And then in a sense, through these graphs that's highlighted here, the history of the universe, and then finally gravity waves. So I want to go back to this. That was right at the very first thing, but I think this talk, I hope, has shown the truth of what Neil deGrasse Tyson had to say, which is that in practically every idea we have as humans, the older version of it is not better than the newer one. With the invested effort of generations and centuries and sometimes millennia of smart people who've been born since the idea came out, we have improved ideas. And this certainly shows, I think, the improvement of ideas from the Greeks to what we're able to talk about now. So stay tuned for another 4.5 billion years. That's about how long our sun will continue before it's used up all of its hydrogen, and then will expand and burn up Mercury and Venus and get the Earth will be very toasty, and then it will shrink down and become a white dwarf and just hang around as a white dwarf, and over many millennia get colder and colder and colder. So this has been a Barn and a BPA collaboration, and we're going to send out the video link to tonight's talk, but in that's going to be a little question for us that'll help us put together future classes. So you could maybe comment on the format, the subject matter, whether our approach was too basic or too advanced, whether the sessions are too long. I'm sure this one's too long, and any other comments that you might have. And finally, stay tuned and sign up for Frank's talk on the introduction to optical telescopes and how to use them. That you can do at the Barn website, and it's free for Barn members and a small fee to other people. And I've had a lot of fun doing this, and I thank you all.
All right, thank you, Peter.
Thanks.
Let's give Peter a bunch of clapping hands here.
You can ask further questions. We haven't signed off here. If somebody's got something they want to ask.
I just wanted to say I really liked the way you presented it. You gave real technical information for those who wanted it, and then you also gave information that someone who doesn't know a lot about this could understand it. So I really enjoyed the videos and the graphics, because that's how I take in information.
Yeah. Well, thank you. I'm a visual guy myself, but I also am sort of a wordy person. But so I combined those two things a little bit. And but the videos, as you saw, that are available are just fantastic. I mean, what can be done now is great. And there was no point when we started thinking about this, well, I'll get this slide and I'll get that slide and blah, blah, blah. You realize it's pointless. You get good quality stuff and just merge it in. So thank you.
Class.
All right.
Okay, well, it's later than normal. Well, not too much. We're
Not
7 minutes late.
I would just like to say, as a proud English major, I really enjoyed this.
Good for you. Good for you. Well,
it was great. Thank you.
well, it's a wonderful subject, and trying to make it accessible to people, I think, is really cool. I've, as you know, I got introduced to it when I was very young, and it had a big impression on me. And we don't have any young people in this audience. I don't, well, never mind. I won't go there, but we don't have children.
Everything's
anymore.
relative.
Well, from your perspective, Peter.
Yeah, from my perspective, you're all young, but anyway.
Yeah, I think you've done a wonderful job. This whole series I thought was amazing. You talk about quantum mechanics at a level that English majors can enjoy and be interested and captivated by. So
Yeah.
I think you've done a wonderful job of presenting complex material to the layman.
Well, thanks, Tim.